Hello learners! In the previous episode, we learned about some important compounds of boron and aluminium along with their uses. We also gathered the basic knowledge about the elements of group 14 such as their electronic configuration, trends of radii, ionization enthalpy, etc. Now, let us continue our discussion with the chemical properties of elements of group 14 and some allotropes of carbon. After this discussion, you will be able to explain the oxidation state and the trends in chemical reactivity of the elements of group 14, the reactivity of group 14 elements towards oxygen, the reactivity of group 14 elements towards halogen, important trends and anomalous behavior of carbon, different allotropes of carbon, namely diamond, graphite and fullerenes. Let us start this session with discussion about the oxidation state and the trends in chemical reactivity for the group 14 elements, that is the carbon family. The group 14 elements have 4 electrons in outermost shell. The common oxidation states exhibited by these elements are +4 and +2. Carbon also exhibits negative oxidation states. Since the sum of first 4 ionization enthalpies is very high, compounds in +4 oxidation state are generally covalent in nature. In heavier members, the tendency to show +2 oxidation state increases in the sequence that germanium is less than 10, which is less than lead. It is due to the inability of Ns electrons of valence shell to participate in bonding. The relative stabilities of these two oxidation states vary down the group. Carbon and silicon mostly show +4 oxidation state. Germanium forms stable compounds in +4 state and only few compounds in +2 state. Tin forms compounds in both oxidation states. Tin in +2 state is a reducing agent. On the other hand, lead compounds in +2 state are stable and in +4 state are strong oxidizing agents. In tetravalent state, the number of electrons around the central atom in a molecule, example carbon in carbon tetrachloride, is 8. Being electron precise molecules, they are normally not expected to act as electron acceptor or electron donor species. Although carbon cannot exceed its covalence more than 4, other elements of the group can do so. Why? Well, it is because of the presence of d orbital in them. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. For example, the species like hexafluorosilicate, hexachlorogermanium, hexahydroxy tin exist where the hybridization of the central atom is sp3d2. Next, we will learn about the group 14 elements chemical reactivity. When the members of group 14 are heated with oxygen, oxides are produced. The oxides produced are mainly of two types, that is monoxide and dioxide, with molecular formula MO and MO2 respectively. SiO only exists at high temperature. It is known that oxides in higher oxidation states of elements are generally more acidic than those in the lower oxidation states. The dioxides CO2, SiO2 and GeO2 are acidic, whereas SnO2 and PbO2 are amphoteric in nature, while among monoxides CO is neutral. Germanium oxide is acidic, whereas tin oxide and lead oxide are amphoteric. When we study about the reactivity of group 14 elements in water, it is observed that carbon, silicon and germanium are not affected by water, while tin decomposes steam to form dioxide and dihydrogen gas. Lead remain unaffected by water, most probably due to the formation of a protective oxide film. The elements of group 14 can form halides of formula Mx2 and Mx4. All members react directly with halogen to form halides under suitable conditions except carbon. Most of the Mx4 are covalent in nature. The central metal atom in these halides undergoes sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are tetrafluorotin and tetrafluorolead, which are ionic in nature. Do you know that lead iodide does not exist? And do you also know why? Well, let me tell you. It is due to the fact that lead iodide bond initially formed during the reaction does not release enough energy to unpair 6 s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atom. Owing to this very same reason, heavier members germanium to lead are able to make halides of formula Mx2. You must be wondering that even these halides are stable or not? Well, stability of dihalides increases down the group. Considering the thermal and chemical stability, germanium X4 is more stable than germanium X2, whereas PbX2 is more than PbX4. Except for tetrachlorocarbon, other tetrachlorides are easily hydrolyzed by water because the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Hydrolysis can be understood by taking the example of tetrachlorosilicon. It undergoes hydrolysis by initially accepting lone pair of electrons from water molecule in d orbitals of silicon, finally leading to the formation of tetrahydroxysilicon as shown on your screen. Like first member of other groups, carbon also differs from rest of the members of its group. It is due to its smaller size, higher electronegativity, higher ionization enthalpy and unavailability of d orbitals. In carbon, only s and p orbitals are available for bonding and therefore it can accommodate only 4 pairs of electrons around it. This would limit the maximum covalence to 4, whereas other members can expand their covalence due to the presence of d orbitals. Carbon also has unique ability to form p-pi multiple bonds with itself and with other atoms of small size and high electronegativity. Few examples of multiple bonding are C double bond C, C triple bond C, C double bond O, C double bond S and C triple bond N. Heavier elements do not form p-pi bonds because their atomic orbitals are too large and diffuse to have effective overlapping. Carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. This is because carbon bonds are very strong. Down the group, the size increases and electronegativity decreases, and thereby tendency to show catenation decreases. This can be clearly seen from bond enthalpy values. The order of catenation is carbon much more than silicon is greater than germanium and almost similar to tin. Lead does not show catenation. Due to the property of catenation and p-pi bond formation, carbon is able to show allotropic forms. Due to the unique properties of carbon, it exhibits many allotropic forms, both crystalline as well as amorphous. Diamond and graphite are two well-known crystalline forms of carbon. For a fact, H.W. Kroto, E. Smalley and R.F. Curl were awarded with Nobel Prize in 1996 for their discovery of third allotropic form of carbon, that is fullerenes, in 1985. First allotropic form that we will learn about is diamond. Yes, it is the same diamond that is used for making beautiful ornaments. Diamond has a crystalline lattice. In diamond, each carbon atom has a sp3 hybridization and linked to 4 other carbon atoms by using hybridized orbitals in tetrahedral fashion. The carbon-carbon bond length is 154 picometer. The structure extends in space and produces a rigid 3-dimensional network of carbon atoms. In this structure, directional covalent bonds are present throughout the lattice. It is very difficult to break extended covalent bonding, and therefore diamond is the hardest substance on the earth. It is used as an abrasive for sharpening of hard tools, making of dies, and in manufacturing tungsten filament for electric light bulb. Next allotropic form of carbon is graphite. Graphite has layered structure as shown on your screen. Individual layers of graphite are known as graphene and which are held by van der Waals forces, and the distance observed between two layers is 340 picometers. Each layer is composed of planar hexagonal rings of carbon atom. Carbon-carbon bond length within the layer of graphite is 141.5 picometers. Each carbon atom in hexagonal ring undergoes sp2 hybridization and makes 3 sigma bonds with 3 neighboring carbon atoms. The fourth electron forms a pi bond. The electrons are delocalized over the whole sheet. Electrons are mobile and therefore graphite conducts electricity around the sheet. Graphite cleaves easily between the layers and therefore it is very soft and slippery. For this reason, graphite is often used as a dry lubricant in machines running at high temperature, where oil cannot be used as a lubricant because graphite is thermally stable till a high range of temperature. Last allotropic form that we are going to study about is fullerenes. Fullerenes are made by the heating of graphite in an electrical arc in the presence of inert gases such as helium or argon. The sooty material formed by the condensation of the vaporized CN small molecules consist of mainly C60 with smaller quantity of C70 and traces of fullerenes consisting of even number of carbon atoms up to 350 or above. Fullerenes are the only pure form of carbon because they have smooth structure without having dangling bonds. Fullerenes are cage-like molecules. C60 molecule has a shape like soccer ball and called Buckminster fullerene. It contains 20 6-membered rings and 12 5-membered rings. A 6-membered ring is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered rings. All the carbon atoms are equal and they undergo sp2 hybridization. Each carbon atom forms 3 sigma bonds with other 3 carbon atoms. The remaining electrons at each carbon is delocalized in molecular orbitals, which in turn gives aromatic character to the molecule. This ball-shaped molecule has 60 vertices and each is occupied by 1 carbon atom, and it also contains both single and double bonds with carbon-carbon distances of 143.5 picometers and 138.3 picometers respectively. Spherical fullerenes are also called buckyballs in short. It is very important to know that graphite is thermodynamically most stable allotrope of carbon, and therefore formation enthalpy of graphite is taken as 0. Formation enthalpy values of diamond and fullerene C60 are 1.90 and 38.1 kJ per mole respectively. Other forms of elemental carbon like carbon black, coke and charcoal are all impure forms of graphite or fullerenes. Carbon black is obtained by burning hydrocarbons in limited supply of air. Charcoal and coke are obtained by heating wood or coal respectively at high temperature in absence of air. To conclude this session, let us recall all the discussed concepts. The first point is the group 14 elements have 4 electrons in outermost shell, and the most common oxidation state exhibited by these elements are +4 and +2. Although carbon cannot expand its covalency beyond 4, other element can do so due to the presence of d orbitals in them. When group 14 members react with oxygen, they form oxides. Group 14 elements form halides of formula Mx2 and Mx4, where X is equals to halides. Carbon shows anomalous behavior due to its smaller size, higher electronegativity, higher ionization enthalpy and unavailability of d orbitals. Physical properties along with structure of allotropes of carbon such as diamond, graphite and fullerene was also studied. Before ending this session, let me leave you with some questions to figure out. The question number 1 is, why hexafluorosilicate is known and hexachlorosilicate is not? Second question is, why diamond has high melting point although it is covalent in nature? So, learners, that is all for this discussion. We will continue our discussion in next session. Till then, happy learning.